So, great to have you all here, given the tough competition that we have between great talks in this summit. My name is Villu Ruusmann, and I am the founder and CTO of a small Estonian company called Openscoring. As the name suggests, this company is in the business of providing open source Java libraries for the development of data-driven or predictive apps. The vast majority of our use cases relate to the deployment of R and Python models on JVM-based data frameworks such as Apache Hadoop and Apache Spark. So, why would you choose Java in such a situation? Basically, it's all about designing a workflow that facilitates communication and reduces technological friction. As the organization grows, people and their roles become more specialized. There will be data science people that know all about machine learning methods, and there will be DevOps and IT people that know all about the latest information systems. And your ability to deliver data-driven products depends on your ability to ensure good overlap between those two groups of people. If you're looking to scale up a system, then it's critical to realize that there are many moving parts to it and that each part has unique scaling properties. The challenge is to identify and work around the limiting parts. For example, if you simply add hardware, then you can expect to grow perhaps 1 or 2 orders of magnitude, because most of those added hardware resources are used pretty inefficiently. However, if you diligently work to identify and work around the limiting parts, then you can reasonably expect to grow many more orders of magnitude, and the system as a whole will be balanced and stable. In this case, the limiting part is about communicating the algorithmic description of the predictive app. As those tools and technologies that you can use in desktop environment for training the model are not so suitable for model deployment in server-side and cluster environments. Basically, the primary objective is to be able to mark down the algorithm so that it could be automatically recreated and executed on most diverse environments. Also, somewhere around here lies a great opportunity to reconceptualize models from the business perspective. A model is not just an R or Python script that delivers you scores. The model is a condensed knowledge about your data, and as such represents a new kind of intellectual property. Basically, a model should be regarded as a launchpad for new business ventures. The communication of machine learning algorithms is not a new problem. A consortium of major software vendors called the Data Mining Group has been working on relevant standards for close to 20 years by now. And today you can choose between 2 standards. The more established one is called PMML, which stands for the Predictive Model Markup Language. The new contender is called PFA, which stands for the Portable Format for Analytics. The main difference between the two is the abstraction level. PMML is a high-level language which provides a fixed vocabulary of domain-specific concepts. PFA, on the other hand, is a medium to low-level language which feels rather similar to common programming languages. Given this choice, my experience tells me that you should always go with the higher abstraction level, because this way you will be much more productive during the development stage, and you will have much easier life during the maintenance stage, because you have a pretty good chance of being able to automate your operations. So PMML is perfectly good standard for making a connection between the state-of-the-art data tools and frameworks. The PMML connection is a fixed complexity proposition. It means that it takes exactly the same amount of work to deploy R models on Apache Spark as it takes to deploy Apache Spark models on Android. In both cases, the turnaround time is measured in minutes. Another interesting opportunity is the ability to connect different versions of the same software, as it greatly simplifies software upgrades cycles. So in this point, I hope that you all agree with me that standards show great promise for making tight data science workflows more convenient. However, a standard in itself is just a normative document. It needs to be implemented and packaged as an API product before it can make real impact. I have a reason to think that my company has come up with a reasonable and easy to use model API, and during the rest of this talk I will be showing you how this model API looks from the end user perspective. This model API is not a monolith. The pipeline can be broken down into three main segments of conversion, maintenance, and deployment. The biggest innovation is the introduction of a special purpose maintenance segment, which is concerned about tracking the health and performance of a model over the extended periods of time. Within each segment, there are standalone components for integration with specific data tools and frameworks. Most of the components are feature complete and production quality, so your only responsibility is to pick the right components and connect them the way you want. Conversion deals with translating the model from the proprietary representation to the standardized representation. The conversion of the model object, which is central to everything, is rather trivial because it's about copying information from one data structure to another. The conversion of associated data flows it requires more thought and human involvement. The goal is to grow layers around model object so that it would become easily interfaceable with your current and future data assets. And the success metric for conversion is the amount of glue code that you have to write during the life cycle of your predictive app. And if you do a good work, then you can get away with writing no such code. Also, I think that there is a great analogy between navigating a maze and training a model. In both cases, you know that there is a path forward, but you are forced to find it out by trial and error. For example, during model training, you need to take excursions around feature engineering, choosing the right machine learning algorithm and tuning its hyperparameters. However, the exact path of your search activities is completely irrelevant long term. You only need to capture the checkpoints that correspond to the endpoints of your search activities. The next time you enter this maze, then your goal is to move from one checkpoint to another using the shortest and straightest path possible, even if you are required to kick down a few walls here and there. So during the conversion, you need to convey the green path. The fragments, well, you can and you should ignore the fragments of the red path from now on. You can safely leave those into your R and Python scripts as supporting information. Conversion produces a model representation that is fully decoupled from the original data tool. For example, all these R and scikit-learn classifier objects collapse to the following PMML representation, which is equally approachable for humans and machines. And despite its apparent verbosity, this representation can be more memory efficient than R's and Python's internal matrix-based representations. The standardization turns models into reusable components, which opens up ways for new and exciting developments. For example, the following 5-line script builds a weight classifier by combining 5 parts of an XGBoost model with 2 parts of neural network model and another 2 parts of random forest model. With this kind of ensemble, you have a pretty good chance of scoring high points on data science competitions. Maintenance deals with formalizing the expected life cycle of the model. In brief, you would define a set of model states and implement automated transformations for moving from one state to another. In the standardized state, the model is re-encoded according to organization's style guide so that it would be maximally easy to comprehend for humans. Admittedly, the quality of PMML conversion software varies, and so you do not want to waste your time on dealing with substandard variants. In the enhanced state, The model is periodically scored with the latest snapshot of your data, and the performance metrics are calculated and stored with the model. By observing performance changes over time, you will have a pretty good understanding if a model is still fit for production use or not. In the optimized state, the model is re-encoded so that it would be maximally suitable for execution on the target platform. For example, in some cases, it may be appropriate to translate the model to native application code. The proposed model maintenance system can be implemented very easily. For example, you could use a simple Git repository for this. During deployment, the model is exposed just as a function. The function takes a number of arguments and produces a primary response. The primary response is a live object that can respond to specific feature queries, producing secondary responses. For example, for classification type models, the primary response is the predicted class label, and the probability distribution across all class labels is one of many secondary responses. The model comes with exhaustive metadata. Basically, each argument and response fields of the previously mentioned function has a machine-readable description, which involves name, data type, operational type, the full description of valid and invalid value spaces, and much more. This kind of metadata serves very well for model documentation purposes, and it can be used to automatically assess if a model is compatible with some specific data asset or not. Here, the goal is to prevent evaluating the model with invalid data records or with data records that fall outside of the intended applicability domain of the model. Model evaluation is an atomic operation where you pass a dictionary of argument values and get back another dictionary of primary and secondary response values. I would argue that this combination of model metadata and evaluation APIs is much more robust and easier to work with than those R and Python APIs. First, the metadata API completely eliminates the need for external documentation. The model performs the preparation and validation of data records automatically without your involvement. Second, the evaluation API is resilient to changes to the structure of your data assets. For example, the model absolutely does not care if you rearrange your columns. However, in your everyday work as a data analyst or a data developer, this finely crafted low-level API will stay hidden from you. Instead, you will be working with high-level model APIs that target specific frameworks. The goal is to get you up to speed with minimal effort. If you already have your model in PMML representation, then you should be able to develop it, or you should be able to deploy it simply by importing an appropriate integration library into your project and writing a couple of lines application code. This figure shows a collection of high-level APIs that we have published on our GitHub project page. Simply substitute the name of the framework into the URL and follow the instructions given in the README file. In the context of this conference, I will show you how it looks and feels to work with some of the highest volume data frameworks. Cascading is an application development platform that provides data flow-oriented abstraction of MapReduce jobs. In order to introduce a model to a data flow, you would instantiate a PMML assembly planner class and identify the data source and the data sync components by name. The configured assembly planner instance is then added to the data flow definition, where it takes full responsibility for generating the low-level cascading pipes and operators. Apache Pig and Apache Hive provide an SQL-like abstraction of MapReduce jobs. In both cases, you would create a user-defined function based on some model document. This PMML UDF contains integration logic, which inspects model metadata and your data store metadata and establishes all the mappings as appropriate. For example, in Apache Pig, you can select all columns using the star operator, and the UDF will be able to figure out the exact subset that is needed. Also, this UDF can be inspected and validated statically before executing the script with actual data assets. So if there is like a problem with the plumbing, you will be able to find it out and take action right away. And finally, the current darling, Apache Spark. Well, the slight trouble with Apache Spark is that it's undergoing active development, and there are so many abstractions to choose from. For example, first you had MLlib and RDDs. Now you have Spark ML and data frames, and soon you will have data sets. Anyway, all those abstractions allow for the column-oriented view of data, and as such are suitable for integration work. For example, you would instantiate a PMML function class and use it as a standard mapper function. Again, as with the previous two examples, we have managed to score an arbitrary complexity model object on a JVM-based data framework with writing approximately 3 lines of code. So, in conclusion, we have applied old computer science wisdom which says that you can pretty much solve any problem by introducing an extra layer of indirection. So instead of trying to make direct connections between X number of model producers and I number of model consumers, we are connecting them one by one to a standardized communication layer. And this approach can be accommodated for new data frameworks as they come along. And the idea of using a standardized data format is this, that, well, there is no vendor lock-in. You will be able to use any other API or toolkit that recognizes this particular standard. So that's all from me. If you have any questions regarding my talk, or if you want to share your experience about how you get your R and Python models to deploy it, then I would like to hear about it. We have one question there.
Yeah, I think it's a great vision to provide agility between model exploration and model deployment. There is still a topic about feature engineering. For example, if you have to multiply two features or compute a moving average on a data stream, what is your recommendation? What framework do you think we should use for feature engineering? Because Openscoring works on a GPN, but what is the best framework to use?
Okay, this question goes back to this conversion. I mentioned that the representation of the model object itself is rather easy, and the difficult part is generating those layers of data pre-processing and data post-processing around it. And, well, even if your R script is, well, let's say that your R script is doing probably a lot of work that is not needed in the end. And so if you want to, let's say, use a multiplication of two variables, then you should just pick out this one line and add it to the description of this standardized model. So, well, I cannot say you that this part is like fully automated at the moment, but well, we are working in this direction, and well, the good thing is that all such converters, they need to be implemented exactly once. Once you have submitted this kind of feature request and this has been implemented, then this functionality will be also available to everyone else in the future. Any other ideas, comments?
Is there an example out there of an R model implemented through a Java UDF&P? Is there an example out there that we could use or play with?
Well, the question is that if there are examples about using R models in Peak. Well, actually, Netflix has been using our libraries to develop this kind of system, and early last year they wrote a technical article about it. They have their own framework developed on top of our libraries, which is called Netflix Surus. But basically the question is, yes, there is a working example which has been developed by Netflix. And well, I guess that, well, time has moved on, and actually today I can provide you with a better integration than the one they described. Okay.
How many types of models can you convert, like from pickles to PMML? You have some
Yes, I was talking about Python in general, but we have been mostly focused on this scikit-learn framework. And I would say that we can do, let's say, about 80% of scikit-learn model types. Well, this basically includes, well, I guess it would be easier to mention the model types that are not yet supported than all the ones that are. But basically, it's the conversion of scikit-learn objects is difficult for a different reason. Well, the trouble is that scikit-learn forces you to think about feature engineering in terms of a pipeline. But this pipeline is very tightly coupled to some sort of matrix data structures. And for example, if you change the order of 2 columns in your input data matrix, basically, well, there will be problems with your pipeline. But we have work around this pipeline limitation, and we are using a component called data frame mapper, which comes from the scikit-learn pandas project, which actually gives you the ability to give names to your columns and, well, and this way start working about this full documentation for models. Any other questions? Okay, this.
Do you have performance benchmarks between the original model in R or Python, for example, and the prediction API that you have?
Okay, this is actually a very good question, because I would argue that you cannot compare those two approaches one by one, because during model training, you have all your data loaded into memory as a matrix, and so you can use all those vectorization operations on it. But when you start deploying on JVM, your data records will arrive one by one. And well, I guess in this case, we could compare how much time it takes to score one incoming data record in Python and to score one incoming data record using this approach. And in this case, I would argue that, well, there is definitely no performance penalty.
And you go to the production side of the house. Can you carry across that transition, or is it up to you to define that as part of how you run the application?
Okay, the question is about using acceleration techniques such as GPUs and stuff. Well, I would say that it's definitely possible, but it hasn't been implemented yet. And the reason is that we regard PMML as a general purpose solution. Well, most of your business needs are related about deploying regressions or decision trees and such low complexity models. And when you start talking about deep neural networks and stuff, then I would say that these are more specialized model types, and a great deal of heavy lifting is actually related to preparing this feature vector. For example, if you have an image file coming in and you need to encode it, then, well, this standardized PMML is not probably the most optimal way of doing it. But if you really want to go for such exotic use cases, then you can always leverage those Java APIs to build a small dedicated encoder or decoder component yourself. For example, if you know that you will be needing such image processing very often, and you have a fixed set of requirements, then you can build this component in Java and plug into this existing framework. One more question.
Yeah, it looks like that since the last time I looked at this project, a lot has changed, and you've done a lot, especially in the area of the kind of model exporting for scikit-learn and ARM stuff. So that's really great. Completely forgot what my question was going to be.
Okay, thanks for the praise.
There was a caveat. I can't remember what it was.
Well, okay, one more. Yeah.
Can you tell us a little bit about your roadmap? We had a discussion, talked about transpiling, and you had some really great ideas. Can you tell everyone about where you're going?
Well, I have no fixed roadmap. I would say that the base framework is in place. And at the moment, I'm like interested in interacting with those real customers to see that where, according to their opinion, that what are the limitations? Because like I mentioned that, well, my goal is to make it like a really easy to use solution. So for example, if you can identify a generally applicable use case which is like limiting for you at the moment, then just let me know and I would be addressing those things. But well, talking about such long-term plans, then it actually depends on where this whole big data ecosystem is going, because I just want to keep tracking all those new and interesting developments and to be able to support all those use cases.
If you've got time, I remember.
Okay.
So it was actually a similar question. It was more about what do you see as limitations of the PMML standard, especially in terms of types of transformations that you can kind of code in that area.
Mm-hmm.
Have you got any thoughts about how you're going to progress?
Okay, the question is again about the limitations of the standard, not about specific frameworks. So, well, this standard is rather open. So you basically have the opportunity to, if some piece of functionality is not yet defined at the standard level, well, you are still free to define your own semantics for the problem and implement it locally. It doesn't mean that, let's say, if there is like a 5% of your problem is not covered by the standard, it doesn't mean that you have to abandon the whole standard. Like with those specialized encoding and decoding components, you can similarly, well, add this 5% to the standard as a proprietary extension and, well, implement the support it yourself. And then you have like the opportunity to propagate your extension to this standards committee and see if it's like accepted in some future version. We have like 1 minute left. If there are no more questions, then, well, you are free for lunch. Okay.